Hello world, welcome back. I'm Andrea and I'm a member of the Elixir core team. This is the 7th video of this series I'm making on network programming in Elixir, where we solve a bunch of network challenges. If you're new here and you want to follow along, start from the beginning, which is linked up here. Today's problem is a bit of a leap in complexity compared to the previous problems we worked through. It required more typing than usual, so I took a different approach this time around. I'm mostly gonna talk, show drawings, and walk you through already typed code. This way, I think we'll be able to talk more about all the ideas and techniques in this video, and we'll have to worry less about mistakes and slow typing. In any case, all the code that I'll show is available on GitHub in a repo that is linked in the description below, so you can always pause the video and take a look at the code in your own time. Cool, let's get to it. So today we're building a speed ticketing system. The description of the problem is way too long to go into detail in this video, but there's a link to the full problem in the description below. Anyways, I'll try to give a summary. We'll build a TCP server that handles two types of clients, speed cameras and ticket dispatchers. Speed cameras are placed at a given position on a given road. They report license plates of cars alongside a timestamp. We can use this to calculate average speed of a given car between two cameras and check speed limits this way. Ticket dispatchers instead are responsible for receiving tickets on specific roads. Our server will have to send the right tickets to the right dispatcher clients. The way that clients identify themselves as a camera or a dispatcher is by sending the appropriate protocol message after they connect. The message also has information about the camera or dispatcher itself. For example, cameras tell the server which roads they're on and at what position. No worries, we'll look at the actual protocol in more detail in a second. If we want to stay at a high level of abstraction, that's pretty much it. The problem specification has a lot more detail, as you can imagine, specifications to do. And that's actually a really good read. If you're new to this sort of network protocols, you'll encounter this level of detail and precision in most network protocols, from databases to HTTP. So this is really great practice. Cool, so we gotta go through our application's architecture next, which is not super straightforward, so I figured why don't we look at the binary protocol first? That way we'll see some code and not just my blabbing face. So when the protocol is not something trivial like a line-based protocol, I like to start from there. Being able to encode and decode protocol messages is a pretty good start and can help with playing around and debugging. In this protocol, serialization is stateless, since we can encode and decode isolated messages without any additional information. Serialization is also pure, which means that the same message is always encoded and decoded in the same way. Because of these very functional, very nice properties, I think it makes sense to put all the protocol code in a separate module. It's going to make it easier to test the serialization, and it's going to keep our business logic and client handling clean from fiddling with bytes. Start with defining a struct for each possible message in the protocol. This makes it really nice to deal with messages in clients by being able to pattern match on fields and have some compiled time guarantees and so on. So I'm going to create the file here, and I'll call it message because it just includes all messages. Okay, so we're starting with a module, and I will start with a single struct for the plate message. So I'm going to define a module inside of this, and I'm going to define a struct inside of the module. And this struct has the plate and the timestamp fields. Perfect. Okay, and the rest of the structs are just here. There's no need to type them out, but it's all def modules inside this main top level message module, and they all have different fields. This one has no fields, and I divided them in ones that are server client, and I should do here client server. So some of these messages are only client to server, and some of them are only server to client. So this problem has a really nice description of all possible data types, such as U8, U16, or string, and so on, and it's only a handful of them. Luckily, Elixir and Erlang's binary handling makes it super easy to work with these. Let's start with encoding, since it's generally easier, since we're the ones generating the messages to encode, so usually there's little to no error handling involved. Elixir and Erlang binary handling is just fantastic. Unsigned integers are just default when constructing or matching on Erlang binaries. For example, a U32 integer can be expressed just with the ::32 specifier, which says that it's a 32-bit integer. Unsigned integers and big endian integers are the default, so we don't need to specify anything else here, which means that if I type : 32 in a binary match, it means that this is an unsigned 32-bit big endian integer. All right. The only non-integer data type in the protocol is the string, str, which is made of a U8 for the length of the string plus the raw bytes of the string. And this is also going to be super nice, so as we'll see in a second. To deal with encoding, we can follow the problem specification. Let's type out the plate message first, and then we'll paste in the others. So I'm just going to go down here. I'm going to say def encode, and I'll match on the plate message, which has a plate and has a timestamp. And we'll just follow the specification. So we start with a single byte, which is 0x20, like 20 in hex. And that's a single byte identifying the message as a plate message. The problem spec says that the type identifier is a U8 and Erlang binary elements default to single bytes. So this is the same as doing this. And as we said, this is by default unsigned and big endian. So we can just do this and we're good. And then we have to follow the message with the plate as a string, and as we can write the string type exactly as specified, which is a single byte for the size. So I can do byte size plate, and this is a single byte. I can omit that. I'll just leave it here for clarity, and then the plate itself as a binary. So this is just going to put the bytes in there, and then the raw string. So it's here, and then the timestamp. Timestamp is a 32 unsigned U32, 32 unsigned big endian. So we can just do that. That's encode. It's really easy to read. Let's just paste in all the others. Awesome. So pasted all the encode clauses in. We don't really need to type all of these out as there's nothing new to learn here. We're just following the specification of the protocol. One thing I want to call out, if you read the spec, you might be thinking, why would you define encode for messages that are only from clients to server? For example, plate is a message that's supposed to only go from clients to the server. So you're right, we really don't need to do that for the server, as messages in this protocol are unidirectional, but it's awesome to have that for tests. So I'm just going to write the encoding and decoding logic for all the messages, regardless of whether they are server to client or client to server. It's a little bit of code anyways, not so much, and it's not going to be a big deal. Next, let's write the decoding side. The coding is just slightly harder. In general, you could divide binary protocols in two categories: the ones where you know the size of the whole messages up front, and the ones where you don't. The protocol we're dealing with is one of those where you don't know the size of messages up front. In this case, the packet option on the socket is not going to help us, and we'll have to do the coding completely by ourselves. The thing to get right in these cases is that we have no guarantees about how TCP packets get split by the network and by the OS stack. We're only guaranteed that all packets are delivered in order, but not how they're split. For example, clients might do buffering before flushing data to their side of the socket, resulting in less TCP packets, each containing more data. The way to deal with this is usually to have a buffer of data for the socket in some state and keep buffering until there's a complete message in that data. This also means that our decoding needs to deal with incomplete messages. It really just sounds harder to explain than to do, so let's just get into the code. So our decode function signature will be this. We're going to say the code takes a binary. It's a binary data, and it's going to return either OK, message, and some others. Message and some other binary, or it's going to return error, or it's going to return incomplete. And I will say when message term, but message is one of these terms. Cool. So the code then takes a binary. Perfect. If parsing is successful, this function will return a full message and whatever data is left after it. If the message is not complete, it'll return the item incomplete. Otherwise, the message is malformed, and this will return the item error. Let's write only one clause to get the idea, and then I'll show you the completed ones like we did before. Let's decode the plate message again, which has a string for the plate itself and a timestamp. Once again, Erlang binary handling in its full glory. So this, if I have this specifier, binary size something, then it's going to match or construct a binary with a specific size, and I can use this exactly to match on the first of the size of the plate as the string, and then the plate itself. So I'm going to write the code clause here by saying, okay, it's the hex 20 number as the first byte, identifying this as a plate. Then it's going to have the plate size as an 8-bit unsigned integer, and then it's going to have the plate, and this is the magic, which is a binary, and the size of the binary is plate size. So very easy to read, very easy to write. And then the timestamp as a 32-bit integer, and then the rest as a binary. Okay, so if anything is left after this, it's going to match the rest of the string or the binary. And then I can construct the message by saying, okay, this is a plate with the plate being plate and the timestamp being timestamp. And I can return, okay, message rest. Perfect. Very easy to read, I think. This is really beautiful to read and to write, very concise and very effective. So the other clauses are pretty similar. The ones that I want to focus on are these last ones at the bottom over here, where we return incomplete if the message looks valid, like the byte is a byte that we recognize as a type of a message, but then the rest doesn't match anything that we saw before, so any full message, and then we return incomplete. And the other one is if we have nothing here, then like the binary is empty, then this is an incomplete message yet. And then we return error if we see a byte, but it's not a byte that we recognize, and it's not a byte in the bytes that specify a type for a message. Also, I want to call out one thing in this code, which is binary for comprehensions. In my experience, it's pretty rare to see those in the wild, but here it makes it really easy to write this piece of code, which is where we have an array or like a list of rows as integers, and the number of elements in this list is here as a U8, as a 8-bit integer, and we can have essentially these rows is going to be a big binary with a bunch of 16-bit integers in it, and I can loop through those and have this binary matching syntax in a for comprehension and just extract stuff. So I think it makes it really nice here to decode a bunch of U16s out of a binary. I promised we'd have tests for this, since the serialization is completely free of side effects and really easy to test. These tests, so I wrote them here, I just pasted them, there's no need to watch me type. These tests take a shortcut, which is that they never really look at the binary data. We only test that encoding and decoding each message results in the original message. So if you see this one, for example, we're just constructing a message, then we are encoding it, decoding it, and making sure that we get the message back. So if I run these tests, first of all, they pass. Yep, perfect. And so we could have a faulty implementation with this testing approach. We could have a faulty implementation of encoding and decoding and still get the tests to pass. But we'll have the Protohackers tests to help us with that and just keep us real, so we won't worry about that too much. So all right, we're good to go on the protocol. We got encoding, we got decoding, we got the messages as structs. We're good to go. So let's talk about our architecture next. The network handling is going to be mostly the same as the previous video, which is linked up here. Let's go quickly over that part of our supervision tree architecture. We have a top-level supervisor for our server. Then we have a connection dynamic supervisor, which is where we'll spawn connections with a socket as we accept them. And last, we have an acceptor task under the main supervisor, whose job is to listen for TCP connections on the chosen port, accept new connections, and spawn connection processes under the connection supervisor. So we'll copy the supervisor, connection supervisor, and acceptor code almost verbatim from the previous problem. So in the acceptor here, I only removed the packet line option because we don't really have a line-based protocol. So the connection is exactly the same. I just changed the name to Speed Daemon instead of mob in the middle as the previous video. And the supervisor here is exactly the same. I just changed the name again. So we got the networking part really out of the way. It's exactly the same as the previous problem. So let's finally talk about how we'll solve the problem, the actual problem, and how we'll architect our OTP setup here. We need a central brain to issue tickets. This brain's responsibility is to determine whether, when a camera reports a plate, there are tickets to be issued. We have several ways of doing this. Our concern is not scalability, so we'll architect the solution to be simpler rather than more scalable. But I'll also mention how we could design it to be more scalable. One of the requirements that helped me design this is that we have different ticket dispatchers responsible for different roads. When the central brain issues a ticket, it needs to know how to send it through to the right dispatcher. We could stick a bunch of state and logic inside the central brain, but Elixir ships with what I think is the best tool for this job, which is Registry. So let's just start from there. So Registry allows us to register processes under certain keys and then look up those processes by key. Registry also supports duplicate values under the same key. This is perfect for us because we'll register each ticket dispatcher in a single registry, a global registry, using the road it's responsible for as the key. A dispatcher can be responsible for multiple roads, which is where a duplicate registry comes in really handy. We'll register each dispatcher under each road that it's responsible for. When the central brain will need to issue a ticket for road X, it will look up all the dispatchers for that road under the key X, in the registry and choose a dispatcher at random. If a dispatcher client disconnects, we'll shut down that process, which automatically unregisters it from the registry. So when I work with registry, it makes me want to write poetry about it for how much I like it. I think it's just great. So let's update our supervisor diagram to add the registry. The registry itself has no dependencies. Connections depend on the registry to be up in order to register themselves if they're ticket dispatchers. It's also kind of impossible in practice for the registry to crash since it's standard library, it's Elixir standard library, and it's simple enough. So we won't have to worry too much about the registry going down and bringing the rest of our server down. Because of these things, we'll stick the registry as the first child under our main supervisor, which is a REST for one supervisor. There is no code. We'll only add the registry to the supervision tree. So we're giving the registry a name. So let's define some options or registry ops. And I will say name, which is protohackers.speeddemon.dispatchers registry. And then we will pass the keys option, keys duplicate, to specify that it's a duplicate registry, as we just mentioned. And really, that's just about it. We'll just start this in our supervision tree with the registry options, and we're good to go. Okay, moving on to this central brain. As I said, we'll want such a thing to be responsible for issuing tickets. Let me make a huge disclaimer. We're working on a teeny tiny problem here. In the real world, we'll be thinking about how to run this application on multiple machines, persisting the data across restarts, and so much more. But here we are, focused on networks and OTP and doing things with the tools that ship with Erlang and Elixir, but just bear all of this in mind, please. For simplicity, we'll go with a single gen server process. It won't depend on anything else, so let's place it as the first child under our server supervisor. Without the central dispatcher, our server doesn't really know what to do, so I'm kind of okay with the fact that if it goes down, it brings down everything else. Now let me get a possible optimization out of the way right away. We could have a single dispatcher gen server per road, instead of a central, unique single dispatcher. A ticket can only be issued for plate observations on the same road, so this would work, and this would also be more scalable, since it would scale up with a number of roads and would be able to calculate tickets in parallel. It also sounds quite doable, since we don't imagine that there would be millions or billions of roads, so one process per road should be feasible. However, this introduces a bunch of complexity, because now we also need another registry to be able to route to the right brain for any specific road, and another supervisor. So we'll just keep this optimization all together here. At least now you know that this is an alternative. I would definitely 100% suggest trying this approach out if you want to get more familiar with OTP and just practice a bit of OTP architecture. I created a file here, central ticket dispatcher, that's what we'll call this. And I also want to start this in our supervisor. So I'll say protohackers.speeddemon.central ticket dispatcher. Perfect. And a comma. Right. And so let's look at this process. So the state of this process is not trivial. So let's just take a look at that first. So this process will keep a map of road ID to road. So before looking at the state itself, let's look at a road. So we'll represent each road as a struct. So I'll just say the module road here and abstract, and it will have an ID, a speed limit, and a bunch of observations on that road. So observations here is a map, and it's a map where the keys are plates and the values are tuples with timestamp and location. So the reason I structured the state this way is that when the central dispatcher receives a new observation from a camera, I want to look only at the observations for that specific road and plate pair. I don't want to really need to recheck other roads, and that's why we're storing the observations for each road with the road itself and not in the global state. This is going to be part of the global state, obviously, because these roads are going to be part of the global state, but it's going to be easier to kind of route to the right roads. And so having this, the state of the gen server now is essentially a single field roads, which is a map that goes from road ID to road. So now every time a camera client receives a plate, it will send it over to the central ticket dispatcher. The central dispatcher will then check previous observations to see if this new observation results in any tickets. Calculating tickets now is not really interesting, and it's not network related or OTP related. So I'll just quickly show you the code that I wrote to do that. So the first thing to notice is that I added a name to this gen server, so that it's registered under this name. And this is so that the dispatchers can send calls to this gen server without knowing its PID. They can just use the name. And I also added a bunch of functions that are part of the public API here. So add the road is going to be a function that a dispatcher, that a camera calls when it connects. So it's going to say, oh, I'm responsible for this road, and this road has this speed limit. So register this road if you haven't got it already. And then register observation. This is the function that camera clients will call when they receive a plate message. So they'll call this function on this central dispatcher, and this function is gonna take the road and the location of the camera and the plate that was recorded and the timestamp it was recorded at. Then there's a bunch of code that handles all this stuff and handles the casts where we add the road and register the observation. So we'll go through this code in a second. The only interesting thing about this code is how we retrieve the dispatcher for a given road, which we do somewhere around here in the bottom. Yes, there you go, where essentially when we want to dispatch the tickets to the available dispatchers for a given road, we call registry.lookup on the dispatchers registry and we pass the road ID, and this is going to return a list of dispatchers that are registered for the road. If the list is empty, we kind of keep this ticket for later. We'll go through that in a second. If we have dispatchers for that road, we'll just pick one at random and then we'll just do our thing. I'm not going to go through this code right now because there's some things to figure out, but this is the only really interesting piece. There's something I haven't touched on yet. The problem specification says that we could also emit a ticket when no dispatchers for the road are currently connected. In this case, we're supposed to hold on to the ticket until the dispatcher for that road comes online. Usually you want a more complex setup here, or you maybe queue tickets and persist them somewhere, but we'll skip all of that. We'll hold these pending tickets in the state of a central dispatcher instead. However, how are we going to know when a dispatcher for a given road comes online? Just lovely sweet registry again. You can give an option when starting a registry that's called listeners. This is a list of named processes that receive events about when new processes register or unregister on that registry, which is exactly what we need. We'll know when a new dispatcher comes online, and we'll go through the pending tickets to flush the ones for that road. So yeah, now this code should make a little bit more sense. The first thing that I did was adding a pending tickets field to every road. So every road is now going to have a bunch of tickets that have not been sent yet because there were no dispatchers for that road available when the ticket was issued by our central ticket dispatcher. So now we can use the listeners option in our registry. So I'm going to go to the supervisor and I'm going to add this option here. It's going to go listeners, and I'm going to essentially pass this in as a listener to events for this. And then there's this little piece of code that handles the notifications or the messages from the registry. So we handle them in our central dispatcher. When a dispatcher connects, we can dispatch the tickets for that road. So which is what we do here. If we see a register message and we have a road ID as the key under which the process is registered, the dispatcher is registered, we can call this dispatch tickets to available dispatchers function, which is actually going to do the dispatching. We don't really need to look at that too much. And if we get an unregistered message, which means that the dispatcher disconnected, we don't really care in its central ticket dispatcher here. We'll just ignore the event essentially. So all the code to generate tickets, as I said, is not very interesting. When this generate tickets function actually takes a road and a plate and it checks if there should be a ticket for that road. So it does stuff like sorting all of the observations, deduping them so that overlapping timestamps can be squashed together essentially. And then it zips the same observations list shifted by one essentially to get pairs of observations, and then it checks the pairs to see if the speed is too high, and if it is, then it returns a ticket. And then we have this function dispatch tickets to available dispatchers, which is down here, where we do what we just looked at it a little bit before, but it's essentially, this is the important part where we go through all the pending tickets for that road, and then we just send them if they are, if we can, we send them through, we cast to the dispatcher that we fetched from the registry, and we send that ticket. The little thing here is maybe worth noting is that the problem description says that we should just not send tickets more than once per day per car. And to do that, this is really not interesting, but I'm just doing I'm just storing the ticket start day, which is just like the timestamp divided by 24 hours in seconds. and the plate in a field in the states, this sent tickets per day. And the first thing I do is like, if there is already a ticket with that plate in this field in the state, then don't send the ticket. This is really not very good because we're not ever cleaning this up. The problem description says that we should not consider our server's timestamp. We should just consider the timestamps that we get from the clients. So it's really kind of hard to figure out when should we clean this up, when should we sweep the state and these sent tickets, and we technically can't because the server doesn't know anything about timestamps. We could do a little bit of smart logic to say, okay, if we get observations that are, if we get non-consecutive observations, we can probably ignore the previous ones, because if they didn't result in a ticket, they will not result in a ticket for that road. So we can do a little bit of smart logic, but I figured we're already covering a lot of stuff. Let's just get through the problem, and I'll shut down the server for this Protohackers problem before this can become a memory leak. But this would be a memory leak, a proper memory leak, if we wouldn't clean this up. So if you're implementing this right, then I would recommend figuring out a way to clean these up and to clean the seen tickets up, periodically or something like that. Finally, we're left with our connection process. This represents a TCP connection to a client that can be either a camera or a ticket dispatcher. In a similar but more complex case, I'd probably use my favorite module in the Erlang standard library, which is gen_state_m. A client, after all, is a state machine here. For example, it can only receive a IM camera or IM dispatcher message if it hasn't received neither of those messages yet, essentially starting in a kind of type unknown state. Another example is that a client can only receive a plate message if it's a camera, so only if it's in the camera state. However, gen_state_m would be yet one more thing to go through, so let's just stick with the gen server. To implement the state machine aspect, a single type field in the state will just do just fine. We'll set this to nil initially when we don't know if the client is a camera or a ticket dispatcher, and then we'll set it to the appropriate IM camera or IM dispatcher message when we get one. We'll talk about all this code in a second, but let's look at pieces of it. So the first one is this restart temporary on the gen server. I should have used this in previous videos too. I don't know why I didn't, but in general, since these connections, it doesn't make sense to restart them, because if a connection process crashes, it's a process that's handling a client connection. And if it crashes, we close the socket to the client, and there is no way that we can reconnect to that client, right? Like, it's the client that should do the reconnection. So it doesn't really make sense to try to restart this process. So, and saying temporary means that whatever the reason that this process terminates, then the supervisor doesn't try to restart. So that's good to have in general in these cases. Then let's look at the state for the connection, which looks like this. We will ignore the heartbeat ref for 1 second. I'll talk about it in a second. But we'll have the usual socket, which is what we had in the previous problems as well. The type field is what I mentioned, where we store whether this is a camera or a dispatcher, and we store information about that camera or that dispatcher as well. And then let's talk about buffering data, which I mentioned at the beginning of the video with this protocol stuff. And when we talk about the protocol, we saw the messages can be incomplete if the TCP packet is split mid-message. What we do to deal with that is that we just have a buffer of data in the state. So it starts out as an empty binary here. When we receive new TCP data, first we concatenate it to the current buffer, and then we parse as many messages as there are in that data. The new buffer is just whatever is left. And you can see that we do that here a little bit. So we say when we get the data, we just update the buffer in the state, and we use and we concatenate the data that we got. And then here we set active once again, and then we parse all the data, right? And if I go to this function, parse all data, we can see that we decode the message using the whole buffer. And then if it returns a message and something else, then we handle the message and we call parse all data again with a new state. So we took away the message from the buffer essentially. If this message decode returns incomplete, we just don't do anything, because it means that we were not able to decode the full message, or that we finished decoding all the messages, and so we just like not do anything anymore. So this is how we do this sort of buffering part. Okay, so we have a bunch of code to handle the messages from the clients in this handle message function. So for example, here we get a plate message when the client is of type camera, it's like IM camera, and we get a plate message, and what we do is that we register the observation in the central ticket dispatcher, which we looked at before. We have other messages. For example, here we get if we get a plate message and the client is a dispatcher or hasn't identified itself yet, we return an error. And we just have a bunch of not very interesting just message handling here, basically. When we receive a I am dispatcher message, which is over here, this is where we register the dispatcher in the registry under the road as the key. So we call this registry.register function. We give the registry and the road as the key, and then the registry also takes a value which we're not really using here, and this registers the current process under the registry, which is exactly what we want here. So that's kind of maybe the only interesting part about this. Last feature to build is heartbeats. The problem says that clients can request to receive heartbeats at a given interval. When you have recurring things to do in a process in Erlang and Elixir, you'll generally have two choices, which are timer.sendAfter or timer.sendInterval. With sendAfter, the pattern is this. You send yourself a message after the interval time, and when you handle the message, you just call sendAfter again. It's sort of like using active ones for sockets, and this is a good pattern when you want to avoid accumulating these tick messages. You will only schedule a new one if your process was able to handle the previous one, providing some sort of back pressure. With sendInterval instead, the runtime sends messages to your process at a specified interval, so those messages could accumulate if your process gets stuck doing something. However, this function avoids time drift since the messages are at least emitted at a regular interval. So we'll go with sendInterval here because it's simpler. We don't really care about back pressure or precision here, so why pick a more complex solution? The only thing to note in this code is that if we receive a want heartbeat message and the interval is 0, we should cancel the heartbeat. So the whole code is in this function. So these timer functions always return a reference, a timer reference that we can use to cancel timer. So this is what we do here. If we have a heartbeat ref, a timer ref in the state, first of all, we cancel that timer, so we start from scratch. And if the interval is basically not greater than 0, the interval is 0, then we just not have a timer. We cancel the timer already, and we don't set up a new one. If the interval is something greater than 0, then we call timer.sendInterval, and this returns a heartbeat ref that we store in the state. And then we have this send heartbeat message that we handle over here, where when we get this message, we just send this message heartbeat to the connected client. Okay, I'm contractually obligated to mention tests here. The protocol tests were really easy to write. Writing stateful tests with multiple clients is a bit less comfortable, but let's take a look at a couple that I wrote. Integration tests here, since Protohackers is going to do all the heavy loading for us and test a bunch more corner cases. However, we want to make sure that this thing at least sort of works. So the tests here are nothing special, and they're quite similar to the ones that we wrote in previous videos. Opening sockets to simulate clients, and sending messages and asserting that they receive server messages. So it's pretty straightforward. It's kind of similar to what we had in previous videos. If I run mixed test, once again, well, they all pass. So this is just to have something that checks that this is not completely broken. So you know what? We're done. Let's just deploy this whole thing and check it with Protohackers. I already updated the configuration for Fly to open the right port, and I already deployed this. So we can go ahead, we can go to the Protohackers problem description, I can scroll to the bottom and I can check this. So we're gonna skip to when it works, but this should work. Cool, it works. So one small thing that I want to call out that I really love in this code is logger metadata. I really love using that. So here I'm doing stuff like I'm setting the type of in the logger metadata, I'm setting a type metadata to dispatcher, or I'm setting it as a camera somewhere else here, and I'm doing logger.metadata. For example, for cameras, I'm also putting the road in the metadata and I'm putting the mile. So if I go into the configuration here and I configure, for example, the console logger backend to include this metadata, then it gets logged when when this process is automatic. It gets stored in the process dictionary. The metadata gets stored in the process dictionary, which means that every time, for example, I log something from a connection, it's going to log the type of that specific connection. And if it's a camera, it's going to log the road and the mile. which is really, really handy for debugging. And it's something I really try to do every time I can. It's amazing. So one tiny disclaimer, not all of the code that you see in the video and that I show in the video is exactly the same as the code that is on GitHub. Sometimes I have to go and touch up the code, or I have to do little changes to make the tests work again after I do some refactoring and stuff like that. And sometimes I forget to check. So it's not going to be exactly the same as the one that is in the video. So if you see something in the video and you're like, oh, this, like I did exactly the same thing and exactly the same code and it doesn't work, it might be that I changed it. So always go check on GitHub to make sure that you're like, that's the code that I'm actually running and it's actually deployed on Fly.io to actually test against Protohackers. So I forgot one thing. Do let me know if you prefer this format where I show more drawings and where I kind of talk about the architecture and the LTP architecture and talk about the concepts and, you know, kind of more about ideas and just show already typed code, or if you prefer the format where I type out all the solution in the video. So let me know which ones you prefer, because I think this one worked pretty well, but who knows. So you made it to the end of this video. Congratulations. I really loved working on this problem and filming this. I think we went through a lot of stuff here. The network aspect of this problem wasn't very complex or anything, but the problem really allowed us to explore OTP concepts and patterns. I especially love being able to work with Registry. I think it's one of my favorite parts of the Elixir standard library. I hope you got interesting information out of this. If you have any questions or feedback, leave a comment down below or reach out in any other way. Thank you so much for sticking with me here, and I really hope to see you in the next one. Cheers!